All right, I'm going to give you your joke for the day.
A nomenclature?
That's a good guess. But it's a math concept.
Yeah, I just keep thinking of puns. I just think like anomaly. Like, I don't know.
How many are there?
6?
Okay, which is more than 2, correct?
Yes.
What do we call something in math if it's more than 2? Starts with a P. Who said it?
Oh, a polynomial.
Polynomial, yes.
Polynomial.
Polynomial. At least it got your brain going. All right, Carlos showed up. All right, I'm going to go ahead and get started. Good morning, everyone. If I didn't say good morning once you entered, official good morning to you. I want to take a look at our calendar quickly. I've tried to go in and say what we're going to be covering each day a little bit, at least through Thursday, and then I will update next week once we get done with today. I want to see what information I'm going to cover on the 21st. But you have a quiz over what we cover through today, 4.4 through 4.6 on the 21st, next Tuesday. We'll do some notes at the beginning, and then probably at about 8:45, we'll sign off and you can take your quiz just like we did your test last time, either print it out or work it on your own paper and then send it back to me and I'll grade it and return it to you. So that's the plan for the next quiz. And then hopefully your test will be on the 5th. And somebody was asking how far we're going to get. I'm going to try to get through 5.1. I may have to cut a couple things out, but we'll just see how things go.
Is this quiz still with a partner or whatever?
With a partner? No, it's not supposed to be.
No, like the last quiz last 2 quizzes we were had in class.
Yeah, no, this should be on your own. It'll be just a regular quiz. The one that you worked together was a pop quiz. All right, any other questions before we get started? All right, let's finish up. We had one theorem left. I should have just taken 2 minutes and written it out, but I didn't. So let's start with the last quiz, or last theorem from our last section, 4.5. I'm trying to get Sarah in here. All right, and this one has to do with the dimension of a subspace. Forgot to put theorem out here. All right, this has to do with the relationship between a subspace and a vector space, and we're working with a finite dimensional vector space. So that means the basis has to have a countable number of vectors in it. And that subspace is going to have to be finite dimensional. Hopefully that makes sense. You can't have something that's infinite inside of something that's finite. The dimension of W is going to have to be less than or equal to the dimension of V. And it will equal, the dimensions will be equal if and only if the vector space and the subspace are the same thing. So that's kind of like a subset that's equal to the set. A subset is a subset of it. A set is a subset of itself. So that's the last theorem from that section. I'm not going to use it for a whole lot, but it's good to look at it. Okay, let's take a look at section 4.6. All right, I went through and kind of reworked this section over the weekend. I'm taking most of the theory out of it. So basically what we're going to be doing is computation in this section. It can be a little bit tricky just figuring out which direction to go, but hopefully we'll make that clear enough that and pound it into your head enough that it will be rather easy. Couple concepts we need to review first before we dive in. This is the definition that we had in section 4.4, where we're looking at the coordinate vector of V relative to a basis. So V is a vector in the vector space, and we're writing it as a linear combination of the basis vectors in S. Those coefficients are the coordinates. So C1, C2, C3, etc., Cn, that's the coordinates of V relative to S. That's a C, not a V. So that's the first thing I want to remind you of. In matrix form, it looks like this. And we'll be looking at both forms today.
You said relative to V.
All right, the other thing we need to review is that a vector space can have more than one basis. And sometimes it makes life easier if you can change from one basis to another. So that's what we're going to try to do. Now I've changed things up a little bit from the way the book writes them. It's not wrong, it's just that I changed the direction, hopefully to make it a little easier to follow. So here's how we're going to do a change of basis. That's an N. These are primes, just like you would use in calculus, like F prime. But our old basis is U1 to UN. Our new basis is U1 prime to UN prime. And this is the relationship between a vector written relative to B. So this is the coordinate vector of V relative to the old basis. This is the coordinates of vector V relative to the new basis. And then we have this matrix here called matrix, it's matrix P, that is the transition matrix. And once we get to the next page, I'll tell you how we're going to find that. I don't know if you guys are done or not. Can't tell.
To be clear, these are not vectors in our vector space. They're called again?
V is a vector in the vector space, but these expressions here are that vector relative to the old basis and the new basis. So these are coordinate vectors. All right, I'm going to assume people are done. Haven't heard anything else otherwise, so all right. Okay, so if you want to find, refocus here, hopefully, there we go. To find the transition matrix P, and this tells where you're going from and to. So we're going to go from the old basis B to the new basis B prime. So we're going to take U1, which is the first basis vector in our old basis, and write that as coordinates relative to B prime. Do the same thing with each vector in that first basis, in the old basis, write it in terms of coordinates of the new basis vectors and write those as columns. That will be our transition matrix. Okay. This is just a note that if you want to work the opposite direction, you can. And that's what P looks like if you go the other direction. So if you go from what we're calling the new basis to the old basis, everything switches around. I just want to make sure you have that in your notes. Okay, I think it'll be a lot more clear if we do an example. So let's go that route. Let's do an example. So here's a vector space in two bases. We're going to say this is the old one, this is the new one. And the first thing we want to find is the transition matrix that goes from B, our old basis, to B prime, our new basis. And this is what it looked like before. We're going to take the first vector in our old basis and write it relative to our new one. That will be column 1. We're going to take the second vector in our old basis and write it relative to the new basis. Those coordinates will make up the second column of our matrix. This right here is what you have to remember in order to do these problems. You're always going to write the old basis vectors, whatever those are, relative to the new basis vectors, and that's what gives you the columns of your transition matrix. Okay, so the first thing we want to find is U1 relative to B prime. So I'm going to take the vector, the ordered pair, the vector 1, 2, and I want to find what that is written as a linear combination of the new basis vectors, these vectors right here. So I'm going to say 7C1 plus 4C2 has to give me 1. So I'm taking the first component, 7C1, 4C2, and that gives me the 1 here. And then the second one is going to be 3C1 plus 2C2 gives me 2. Okay, as a system, it looks like 7, 4, 3, 2. 1, 2. And if you put that in your calculator and put it in reduced row echelon form, what you're going to get is 1, 0, 0, 1, -3, and 11 halves. So the coordinates of that old vector relative to the new are -3 and 11 halves. So I'm going to say u1 relative to b prime is -3 and 11 halves. Okay, that's column 1 of our transition matrix. -3, 11 halves is this column of our matrix. Okay, let's do the other one. Raise your hand if you're not done. Okay. Let's do the next one. So I'm going to take the second old basis vector, which is 3, 4, and write it as a linear combination of the new basis vector. So I'm going to have the same system. These won't change. But the old basis vector on the other side will. Now I want it to be 3 and 4. And I got to refocus. Come on, phone. There we go. It focused for a second. There we go. Okay, I'm going to set that up as a system. 7, 4, 3, 2, 3, and 4. And if you put that in reduced row echelon form, you get 1, 0, 0, 1, -5, and 19 halves. That means that u1 relative to b prime is -5, 19 halves. So now I know my transition matrix from B to B prime. The first column is U1 relative to the new basis vectors, which was -3 and 11 halves. And then the second column is -5, 19 halves. So any vector in relative to the new basis will be this matrix times B relative to the old basis. That's how I would translate a vector in relative to the old basis to a vector relative to the new basis. All right, part B of this is if we have a vector -2, 1 relative to B, so this is the coordinates of vector B relative to, coordinates of vector V relative to basis B. Now we want to find V relative to B prime. So I'm going to write what I had earlier. Actually, I won't. I've already got it up here. So I'm going to take -3, -5, 11 halves, 19 halves times this vector, -2, 1. And that will give me that vector relative to the new basis. All right, when I calculated that, I got 1 -3/2. We don't even know what the vector is, but we know what it is relative to the old basis, -2, 1, and what the coordinates are relative to the new basis, which are 1 and -3/2. Okay. What did you notice about the two systems that we solved? What was the only thing that changed?
The constant terms.
Yes, the constant terms, right? So we could have, we could be in 5 space. We would have exactly the same 5 equations, only the constants would change, and we could do that 5 times. Okay. Now, one of the things that we talked about back in section, way back in 1.6, is we can find solutions to a bunch of systems at once. Oops, I just spelled the wrong word wrong. So we can solve a whole bunch of systems at once. All we do is augment more than one set of solutions. And solve it. And then what we're going to get is the identity matrix here. We'll get solution 1 here, solution 2 there, etc.
I just realized that we started calling the subsets B because it matches the way we called constant vectors before. Or
Good insight. All right, so rather than do all these individually, which you're going to have some homework problems where they have you find individual vectors like this. But if you want to find the transition matrix, we can find that in one shot if we let A be the coefficients of the new basis vectors, right? Those are the coefficients from our system. And these over here are our old basis vectors. If we put that in reduced row echelon form, we will have our transition matrix over here on the right side. Just writing what I said a minute ago. So if you set up a matrix where you have your new basis vectors on your left-hand side, your old basis vectors written as columns on the right-hand side, and put that in reduced row echelon form, you will end up with the identity matrix here and P from B to B prime on this side. So from the example that we did here just a minute ago, we would take 1, 2, 3, 4. Those are the new basis vector. Those are the old ones. 1, 3, 2, 4. No, those are the new ones. Wait, what do I have? Oh, scratch that. I was doing the reverse. We would do 7, 4, 3, and 2. 1, 3, 2, 4. And if we were put that in reduced row echelon form, that would give us P here, sorry, identity here, and P here. I didn't look at what I was trying to do. Okay, so find P from B prime to B for that example. This is what I was supposed to do. So we're going to go the opposite direction this time. In this case, everything's got to switch around. So B prime, we're now treating that as our old basis. What you're going from is your old basis, and what you're going to is your new basis. So I've flipped, just completely reversed what we're going from and to. B prime is our old, B is our new. So we're going to take the old basis vectors, which are 7, 3, 4, and 2, augment our new basis vectors, so the ones for B. Did I just do it reverse? I did. Sheesh, this is the same thing. This should be 1. There we go. These are our old ones now. All right, when I do that, I got negative 19 halves, negative 5, 11 halves, and 3. Okay, take a look at the numbers that are in the two matrices. The first one, we went from B to B prime, and our transition matrix was negative 3, negative 5, 11 halves, 19 halves. And the one we just found from B prime to B is negative 19 halves, negative 5, 11 halves, and 3. How do you think those two might be related?
I would bet that they're inverses of each other.
And I would bet you're right. Good job, Ethan. Yes. If I go from B to B prime, or I go from B prime to B, those matrices are going to be inverses of each other. And I purposely did the 2 by 2 so you can see this. The determinant of this matrix is -1, and that's why you have a sign that looks weird. But otherwise, these two values have been switched. These two are the same numbers, and they're actually the same sign because the determinant is -1. But these two will be are inverses of each other. All right, so let me write out that theorem. If you multiply the two matrices together that we just got, you do get the identity matrix. Just I'll write that out actually. All right, anybody have any questions on those? It can get really tricky just keeping straight what's the old and the new. Obviously, you noticed that when on the last page when I was doing that example. So you have to be very careful, be very diligent about paying attention to what is your old and what is your new. Those can switch if you're doing the reverse part of the problem. But you always write the old basis vectors in terms of the new. So the coefficient matrix that you have will be the new basis vectors, and the solutions will be the old basis vectors. All right, there's one last theorem for this section.
Can you scroll back up a little bit? I can't see.
Okay, this last theorem is a very special case where we're working in Rn, so we're in n space. B prime is any basis for Rn. So think of, like, if we're in 3 space, it could just be 3 vectors that you can generate all of Rn from. And we've had a couple of examples of that. If S, which is your new basis, is the standard basis vectors for Rn, then your transition matrix will just be your regular vectors, because the coefficients of the standard basis vectors will be whatever the old vectors are. If I can find an example of that. Give me a second. Trying to find an example that's got 3 basis vectors in it for R3. I don't know, I'm not seeing one off the top of my head. I'll try to find one of those maybe and post it. All right, who has questions? That's actually it for that section. I did take out a lot of theoretical material. I'll show you what that looks like really quickly. To actually show how to find that transition matrix, this is what it looks like. This is in the book if you want to read through it. It takes that much just to figure out what the transition matrix looks like. But I decided I'd spare you. You guys are really quiet today. So your quiz on next Tuesday will cover the information up through what we've done here. On Thursday, we're going to start talking about the row space, column space, and null space of a matrix. All right, that's it for today.